Okay, welcome back, everybody listening online. So we're going to move on to agenda item 4.1.3 on management strategy evaluation. And so could we have presentation 08 on the screen and through the chair over to Dr. Hicks?
Thank you. As that comes up, the assessment presentation is focused on, I think, what, 2 topics. MSc one's a few more. I think there's about 11 topics, something like that. So after the full assessment, then we move over to the MSc and the operating model. So I'll show you how all of that works. All right. So I'm here today to talk to you about the work that's been going on with the MSc and the Harvest Strategy Policy. We have a framework here to conduct management strategy evaluation that we've been putting together for over a decade now. And it's in the phase now where it's a useful product and just needs to be updated occasionally, and then do all our fun magic with it. So before I get too deep into that, I think it's important to note that we have adopted the Harvest Strategy Policy at the December 15th, I think was the official adoption date. That's a huge success, I think, for IPHC, as well as something I've been working towards for all the time that I've been here. And it's basically describing the framework that we use to manage Pacific halibut, with a lot of different components in it, a real high-level document, just overviewing the management process. And this is a big success because IPHC has never had a harvest strategy policy document before. So this is great, and a lot of great work by the commissioners and everyone involved. The last bullet point on here, it says it also presents a schedule of an annual and triennial process. And so what I want to do is just briefly review that schedule of events. So this little calendar schedule is in the Harvest Strategy Policy, and it shows just what the process is for a lot of different products here at the IPHC. And you see at the very top there, we have the annual FIS, or the Fishery Independent Setline Survey. You see that occurs every year. It also describes the stock assessment process, which you've heard about, with a full stock assessment every 3rd year. And then an updated stock assessment in intervening years. You see that the commission makes TCY-based decisions every year. But what I want to focus on for this presentation is the process with the MSc, in particular the operating model, showing that following a full stock assessment right here, that we will then recondition the operating model based on all the updated information that we've learned from doing a full stock assessment. And that operating model, we take the approach of Doug Butterworth basically told me. He says, get your operating model, put it together, cut it off, and then go do the other stuff that you want to do. In other words, don't get hung up on trying to keep the operating model going, or else you'll never get it done. So we thought, okay, well, maybe we could recondition the operating model every 6 years with a 3-year check-in and just make sure that it's holding up. But also part of the process is exceptional circumstances. We have a number of exceptional circumstances defined, where we're conditioning the operating model this year. So it should meet all those exceptional circumstances because we're conditioning it to those data that we're checking with. And so next year we check the exceptional circumstances, and then we really want those exceptional circumstances to be persistent. So we want to make sure if they're occurred over a 2-year period, then we would reopen the process okay, something's not right with the simulations, it's not matching the data, and we consult with the SRB and the MSAB, present this to the commission, and then open up the MSc process again. So, and I guess the final line that's important here, we've had discussion with the commissioners, is we do want to have the opportunity to update the harvest strategy policy, but that's not something we want to do every year. So the commissioners realize that we'll update that occasionally as we learn new things.
So I haven't had a chance to fully read through the harvest strategy policy stuff yet. But in terms of just strategically planning to relook at your operating model every 6 years, that's basically the schedule we have for International Whaling Commission for all of ours. All of the Aboriginal whale stocks are managed with just MSC-based harvest control rules.
Okay.
And so it seems to work reasonably well for us. And a lot of times even there will be a check-in that we call implementation review every 6 years that we basically say, we review all the stock structure information, we review the other biological information, say, are there things we think we need to test?
Right.
The two main things that we felt we needed to test in the whale world were unusual mortality events, as well as changes to stock structure that have largely come through more expanded evaluations of genetics. And so those have been the ones that have really pushed us for that. So that seems good. For this, when you talk about exceptional circumstances, does that just trigger how a look back at the operating model, or does it fundamentally change how the commission's going to make their harvest decisions?
It's more triggers reopening of the operating model and examining that and finding out why it's not matching the data.
Okay.
The decision-making process in the harvest strategy policy, it states we do have a management procedure, but there's still a lot of flexibility that the commission has in making decisions. So they may see an exceptional circumstance. We may present that to the commission, and the commission may make a decision having that knowledge. But that's not the real purpose of exceptional circumstances. It's to re-trigger. We need to take a look at why the management procedure may not be working. Is it robust, and why the operating model is, or the data and the operating model are no longer. So that's our schedule of events. And so that's defining some of the things we want to do. So here we are in 2026. Looking at the MSC operating model being updated, and then we just want to do an evaluation of the current management procedure that's in the harvest strategy policy and just make sure that's still relevant and robust. So don't get hung up too much here on all the wording, but this is basically the workflow that we use to condition the operating model. We basically look at the stock assessment. We take parameters and assumptions from each individual model from the ensemble stock assessment, and we link that to an individual model in the operating model. So the operating model also is composed of 4 individual models, and that's an ensemble itself. We take a look at all the data that's been updated, including weighted age, different environmental inputs, such as the Pacific Decadal Oscillation, which was completely updated in this full update of the stock assessment. And we just organize all the data around that. We then make sure that make any changes to the operating model executable. And this operating model executable is actually an in-house model that we wrote here, written in C++ for speed. And then we just organize that, make sure we fix any errors that we might have found. We then take parameters from the stock assessment. Some parameters we fix in the operating model, those individual models from the stock assessment, and others we try to estimate. And then we do an estimation routine, more like a conditioning routine, and I'll talk about the data inputs there. And then we have that for each individual model. And once we have conditioned it, then we add uncertainty and create a lot of basically parametric bootstrap as individual trajectories. I think this year I did 1,000 for each individual model, just to have that many. And each individual trajectory would then start a projection. And that's how we get our uncertainty. So I'll show you the results of this process after I talk a little bit about the data that's going into it. So we heard about the full stock assessment. A lot of things were done, including the revised specific decadal oscillation. But one of the major things is that last bullet point is updating the maturity of John. So that's now reflected in the operating model. And that's, another thing you mentioned about the whaling MSE, the whale MSE is, you saw how much research is going on, that oftentimes if we get a whole new fecundity relationship, probably be a good idea to update that in the operating model sooner rather than. So we're flexible in that sense. Okay, so reminder, the stock assessment is 4 individual models that go into an ensemble for that, as Ian talked about, and the operating model is conditioned to the estimated spawning biomass from each of these trajectories. So this is why I call it conditioning, because we're treating these outputs from the stock assessment models as data that we're fitting to in the operating model. Just want to make sure we're consistent with our best knowledge and the full work that is put into creating the stock assessment. So we're trying to match these spawning biomass trajectories. But I guess I didn't have a slide on this. The operating model is actually a spatial model. 4 different areas, the 4 different regions, region 2, 3, 4, and 4B. And so it estimates movement between those 4 regions, as well as how a coast-wide recruitment is distributed to each of the regions. So we need some regional data to fit to. So we take regional observations or estimates from the FIS, the space-time model outputs by region, and we fit to those data as well, as is shown in this plot here. And that's only from 1993 to 2025 and actually there are some observations before then that we are fitting to as well. I can't remember the exact years, but I think it goes back into the 19s. We're also fitting to regional age compositions, but there's, once you put in age compositions, there's a lot of individual observations that overwhelm your likelihood. So those are down weighted, as they are in the stock assessment as well.
Is it the same procedure?
No, it's more ad hoc. Actually, the weighting of all these different data sources is quite ad hoc. There's no real statistical reasoning behind it, other than a lot of times we look at the outcomes and it's like, we don't want it to be overwhelmed by age compositions. We really want it to fit the distribution. So a priori distribution and spawning biomass, I'll show you distribution in a minute, get high weight in the likelihood. And then we will often just adjust them. It's like it's not fitting the end of the spawning biomass time series very well. So we're just like, what, this one, let's see what happens. I'll walk through that procedure in a little bit. And then the 4th data source that we fit to, I'll call them data, these are actual data, is the regional stock distribution. This is the proportion of all sizes, basically WPUE or biomass, you can think of it, in each of these different regions. And so when I say all sizes, that just means all the sizes encountered by the survey. So it's really more like, 5, H5 plus fish, with 5, 6, and 7 being a little bit less selected than this. So it's not really capturing those youngest fish. But we figure this is a very important, there's 2 important sources of data to fit the OM2. One is the coastwide spawning biomass, and that's mainly, the objective here is really to develop coastwide management procedures. So we want to have that movement and that option of that movement to investigate regional behaviors as well. And so because we want to look at it regionally as well, this is another source of data that we find very important, is are we getting the proportions correct in each of these regions, the amount of biomass correct in each of the regions? And then, so those are the two most important. And then we're fitting to the indices, which is an important source of data. And then the age compositions, which is also important, but can be overwhelming. Okay, so those are the four sources of data. The OM, each individual model of the OM, so there's 4 models of the OM, are then conditioned to each of those 4. Each of the models in the OM starts in 1958. So we don't have short and long models in the OM, but we're fitting those to short and long assessment spawning biomass outputs. We're estimating movement from region 4 to 3, and then from 3 to 2. And that's the only ones that we're estimating. All others are fixed and assumed fixed, and they actually have small amount of movement. And we're also not allowing annual movement in an annual time step between non-adjacent areas. So they can't move from 4B to 2. And I'm sorry, Mike, I should have put up a figure of the areas for you. But if you want, we could go over that. Yeah. So they can't move from Alaska to California one time step, basically. But there's been some tags that suggest they move quite far distances in 1 year. Yeah, and so another difference from the stock assessment, well, besides that it's spatial and regional with 4 areas, is that we add uncertainty and steepness to the operating model. And there's a whole method of adding uncertainty after I do the condition. Basically, I take the stock assessment models, the 2 long ones, and I estimate steepness in it, and I get the its estimate of uncertainty. It actually does a surprising. It comes up with a reasonable estimate of steepness, and so I get uncertainty around that steepness, and also its correlation with other parameters that I can then do a parametric bootstrap with. Okay, so I guess I didn't talk, let me just back up and talk about it. So it's described more in the document, but so during the conditioning process, we will fit to each of these 4 data sources independent. So I'll say I'll fit only to age composition. I'll fit only to the spawning biomass, because we want to see what the behavior, what the operating model thinks what each of these data is going to tell the operating model to do. And surprisingly, they're very different. It will fit perfectly to the spawning biomass, and distribution will be great. And I have all these results if you do want to take a look at them. And then you'll fit to distribution, and spawning biomass will be like 3 times higher. So you really have to combine these data sources, I think, to get the best picture. And how to combine them can be challenging. Another thing here is, we're really not seeing this as a strict fitting algorithm for a number of reasons. One, we're inputting spawning biomass, which is an output from a stock assessment, not an actual independent source of data. It's using these data in a sense. And then the second issue is the operating model. We built it as a research model. When I first arrived, Ian had attempted to build a spatial stock assessment model. And it was reviewed by the SRB, and the SRB said, really good job. The model didn't gel. The model didn't come together as a tactical decision-making. There were a lot of issues with it. And we don't recommend it as an assessment model, but we do recommend it as a research model to investigate different things as a simulation model. So we took that and then we created this operating model, but it's confounded. So you have coast-wide spawning. We assume spawning is just one spawning biomass, produces a number of recruits, and then those recruits are distributed to these 4 different regions. Just a simple proportion, and that's estimated in the model. And then those fish have to move. It's totally confounded, right? You could put a lot of fish up there, and then they have to move far. You move some fish here, and they don't have to move as fast. So
6 years.
yeah. Before we have any observation of it as well. So it's the model has a lot of challenges here. So we guide it in the conditioning process based on our sort of a priori assumptions, what we've learned from tagging data that's been published previously. You'll see some of those in some plots coming up. So it's a lot of guidance in there in a sense. Given that, and that, there are a lot of decisions made along the way, it's not fully reproducible, this conditioning process. But I think depending on your starting point and your path that you go, you could probably end up in many different places and get a similar answer. So we try to account for that with the uncertainty, trying to get a reasonable amount of uncertainty. And so what we do is as you notice, not some parameters are fixed in the operating model and taken from the stock assessment. So we do things, like natural mortality is not estimated in the operating model when we're conditioning, it's fixed. So we take the uncertainty from those parameters in the stock assessment and a covariance matrix that has correlations. And then we tack on the uncertainties and the correlations from the movement, and R0 is estimated in the operating model. Can't remember some other parameters estimated in the operating model. So we create this bigger covariance matrix, doesn't have all the correlations, but it allows us to then simulate the parameters from there and create historical trajectories. Now, because of this process, you're going to create historical trajectories that make no sense. Some of them just die. Some of them just don't fit the data at all. And so we have thresholds. It's almost like a SIR algorithm. Really, you create this historical trajectory, you see how well it fits all the data. And then if it exceeds a threshold, throw it out. If it doesn't, keep it in. And we decided the threshold is just, I think it's like 3 times the actual likelihood for each of those data sources, and then summed up over that range. And so we look at how it fits each data source, and if it's exceeding them by like more than 3 times, then we reject. And I think it comes out when you look at it on a total likelihood, it was like, I think it can exceed the total fit to all the data sources by like five times or something. It was 3 to 5, depending how you put it together. But nonetheless, we're just trying to create historical trajectory with uncertainty. So what I'm going to show you now are some plots of different fits to the data for each of the individual operating models. And then I'm going to plot that, which is in red. And I'm going to show you the assessment estimate and its uncertainty in blue. And so we have operating model 1 up here. And the long AAF is the assessment model that this is associated with. So it's saying it's fitting to the spawning biomass. The blue is the spawning biomass from the long AAF model. So it goes back to the beginning of this time series. And you can see it matches quite close, especially at the end of the time series. A little bit of misfit in the beginning, which, there's not really any data informing the operating model back before about 1980, I think. But and so we're not trying to fit that perfectly, especially given the other sources of data. And so that is the fit to the spawning biomass for operating model 1. Then we will show you fit to distribution. And so orient you a little bit. We're starting with region 4B out in the Aleutian Islands, and then 4 is mostly the Bering Sea, some of the Western Gulf. Region 3 is that central Gulf of Alaska, and then region 2 is Southeast Alaska, British Columbia, California.
Are these actually fits of the conditioning, or are these generated from the whole process of then doing the parametric bootstrapping and throwing out bad samples?
These ones are actually from the whole process. And so you're exactly right. There's a slight difference between those. And during the conditioning, so this one, this one fits very well and was very well behaved. You'll see other ones where the operating model is different than the blue line from the assessment. During the conditioning, they were very close. But then this sampling, because you get asymmetry in the parametric, and it causes the median. So I'm plotting the medians here, that they do look a little bit. But the reason that I wanted to plot these is because this is what we'll be using to do the projections. And so I wanted to show what the median, what the central tendency really looked like. So, and I apologize, these are really small, but what's shown on each plot in color is the actual data, and that's with the dot and the uncertainty around those data as estimated in this space-time model. In the black X's are the operating model output. And so you can see, for the most part, they're in pretty good agreement, except there's some mismatch here in region 3 in the most recent years. And so when I started the conditioning process, I've done this conditioning a number of times in my time here at IPHC. So I'm like, oh yeah, that's always the way it starts. And I start tweaking things. I could not get this to fit much better than what you're seeing on the screen. I could not get that to match in those recent years. And we'll talk about that more. And so even if I fit only to these data and I really forced the model to fit those points, it just said, I can't do it the way that the model's currently structured. Can't match those points. So there's about 4 years where all the X's are above the green points. And what it does is it's region 2 in this model fits pretty well at the end of that time series, but then region 4 is under the actual observation. So it's sort of just not quite matching that as well. But no matter what we did, without invoking maybe a new time period or something, we just couldn't get this to match. But in general, it's not too bad. And this is very similar to what we've seen in the past without those recent 4 years. So,
but this model has both constant allocation of recruits among regions and constant movement for later ages among regions, right?
it does. Those two concepts can change with the PDO regime. So and this was actually Olaf's recommendation a number of years ago, when we first started putting this operating model together, we just, with constant recruitment over time, one set of proportions for recruitment and one set of movement, the model just couldn't come together. And we're like, we have to do something time varying. And we talked with the SRB, and it was like, well, why don't you begin to start with putting movement differs by the PDO regime, some environmental variable, basically. So it's either negative or positive. And that actually brought this together well. And so if you chopped off those recent 4 years, you'd think, wow, this is actually fitting really great. Mm-hmm. So it can do that, but I think you're on the right track, is that something has changed potentially that's now causing this misfit in the recent years. And I have a conclusion slide that'll get at that.
Yeah, you're definitely having tension between the beginning and end of years.
Yeah.
Regions 3 and 4.
Yeah, for sure.
Yeah, and we only truly don't know what to be in retrospect, so
Yeah.
it could be in the middle of a switch, right?
Yeah, right. Yeah.
I don't know where we are in the cycle.
Yeah. So I have a couple of slides on
We
that.
are due for a switch.
Well,
If
I'll
it's
show
still
you.
functioning at all.
Yeah, okay.
Let's just say everybody really likes it, because that means we go positive. Okay, so that is I think, yeah, those are the only two fits that I'll show, but I could show fits to other things. The fits to the actual survey indices were not that bad. So here in this plot, and I'm going over this a bit slower because we'll do this for each of the 4 models, but we have here the proportions on the left of the recruitment distribution. So how much of that coastwide recruitment is being distributed to each of these regions, with the lighter color indicating the negative PDO regime, and then the darker color the positive PDO regime. So you can see in a positive PDO regime, slightly more going into the Berings. That's what happens, and then less stay in the Gulf or to 2. And that's not unexpected. You know, we expect a lot of recruitment up in the area 4, and then our hypothesis is there's a ontogenetic movement of fish basically from northwest to southeast. The other 2 plots are the 2 estimated movements, and what's being shown in this, I'll focus on this top left blue plot. That is movement from 4 to 3 in a low PDO period. The gray dots behind the scenes are basically a stitching together of our best knowledge from past research. So I think Ian did this analysis right before I arrived and just looked at all of the research that's been done. Some research was just on the young fish. Some research was just on the old fish. Some research was with this type of tag, you know, so there's all these things, and just brought it together in a quasi meta-analysis way, just to say, this is our best guess at what movement is. So that's the gray dots. And then the blue is what the operating model estimates. And it's basically using a parametric logistic to estimate these movement curves. So it's a little bit rigid in that sense, but it shows somewhat of a similar pattern, but it shows there's no movement from 4 to 3 in those young fish until they become age 4 or 5. And then there's a lot of movement, but as you noted, we don't really have any observations in this to inform 2, 3s, and 4-year-olds. So
That's just from tagging data?
there's no tagging data in here in the operating model. But
I misunderstood that.
The operating model is only fitting to that like distribution and the survey indices by region. And so we're not incorporating tagging into this.
The-
Gray dots are from the tagging,
Gotcha.
and it's not trying to fit to that at all. And so it's just sort of looking at, well, are we telling a very different story than we thought when we put all this together from all of our research, or is it similar in some sense? And I would say, well, it's different, but it's not completely different.
I mean, when you look at it, the cumulative movement up to age 5 is probably pretty similar, right? The model just has them moving later.
Yeah, and that's what I think is happening as well.
At least from 4 to 3, 3 to 2, there's something.
Yeah,
It's just different.
yeah. A plot that I produced a few years ago that I haven't recreated for this operating model yet was sort of a lifetime movement from each area to another area. So sort of like, what is the probability a halibut would move from 4 to 3 over its lifetime? And I think that was pretty informative, but I wanted to go back and do that.
Yeah, I mean, essentially you can look at how much of the cohort
Yeah.
moves over the first.
Right.
That, and it looks like they probably end up about the same.
Yeah. That's actually a good way to do it, is to do it. I was doing it over the lifetime, but doing it up to a certain age.
Yeah, I think what you said before, though, I was confused by what I was looking at here when I was first looking through the materials, trying to understand why you were getting these patterns and what it might mean. But I do think, given your model structure and what you're trying to inform these model estimates with, that you probably do have a lot of confounding between the recruitment proportions and these movement estimates. And it might be worth some thought about ways to try and tease those apart a little bit more. And like, my initial very crude one is start with recruitment at age 5. If that's when you're first starting to see them, get rid of the earlier ages in the model. There's nothing to help inform them. And just start there, and it will make some of these things help work out a little bit better.
Yeah, right. Because there's so much flexibility, 0 to 5. Yeah. Try to do lots of things.
Yeah, especially in this version, if you're not really fitting to the age comp stuff, you're mainly fitting to the overall biomass. It's going to be able to take those wherever it wants. And it might also be one of the reasons why you end up with so many kind of bootstrap versions that do crazy things, because if these will have super high covariances and they might shoot you way off in a crazy space when you simulate.
Yeah, the acceptance rate of those bootstrapping is about 70%. Yeah. So those are the plots that I'll show for each operating model. So I think I was going to say anything else on this, other than it really wants to move the fish when they're young. And then there is a tiny little bit of movement, you know, from 3 to 2 when they're older. But we were talking with the MSAB about this area, or region 3 is where the most amount of biomass and the largest number of fish are. So it's a small rate of movement in a large area. So that actually means a pretty big net input into region 2 from 3, especially if it's occurring over 20 years of a fish's life. There's a high probability that they end up in 2. And I think that's why I created those lifetime things, to see how much could actually move into 2.
And there's really not much evidence of fish going from 3 to 4.
There is a little bit, and that we have fixed movement, but these gray lines, like I said, we've fixed it in the model for at the what we thought was the best amount of movement. But those movement rates are actually really small, less than % or maybe 1% or something. There is some evidence of that backwards movement, but within a year, fish can move quite a bit, but across years, it's generally that ontogenetic movement. There's a paper Piera Carpi did a review on how a few years ago, which is really interesting. Has a circle chord diagram with size of arrows going from each area, and it's really informative. And it does show that there's little movement back, but a lot of movement in that one direction. Okay, so that was probably the best behaving. Now we get into the fun stuff. So this is fitting to the short areas as fleet spawning biomass. And these short models, these short assessment models, they have to start something. And I think what I believe in these short assessment models, there's probably still a couple of years, a little bit of burn in, where it's trying to still settle it in and then predict where the majority of the data are here from, 2000 onwards. And so personally, I'm not too worried about it not fitting the start of that series, and more focused on how it fits the last couple of decades in the spawning biomass. And so what you can see, the operating model predicts from 1958, but is fitting to spawning biomass starting in 1903. It doesn't quite match the beginning, but matches quite well at the end.
At the risk of going too much into the weeds, are the short assessment models assuming some sort of equilibrium at the beginning of their?
They're estimating the initial age structure completely free.
Okay.
And using the catch starting from there. That's because we have a long catch time series and dynamic recruitment. So there's not really any equilibrium that would make any sense there.
Yeah.
It's to be specific, it's the numbers at age in the initial year up to the plus group, and then the slope of the plus group relative to equal. So it's essentially the same number of parameters.
Okay. Yeah, and so, another parameter that the operating model is estimating as well, because it's starting in 1958 when there has been a significant amount of fishing in at least regions 2 and 3. It estimates a parameter, it has an initial amount of fishing mortality, and it estimates a parameter that can adjust that amount of fishing mortality just to sort of bring it into a spot for it to start. And it's also in 1958, it's also estimating the previous 30 years of recruitment. So it's not their input from the stock assessment. And so it is not starting the operating. But you can see it's fitting the end of that time series of spawning biomass pretty well. And the uncertainty is developing basically the uncertainty in the stock assessment. And that's really a goal of ours too, doing MSE to evaluate management procedures that are robust to uncertainty. We want to make sure we're capturing the same or more amount of uncertainty that is in the stock assessment. Here's the fits to the distribution, and it's actually quite similar. There might be a little bit more departure here, but you can see the black lines in region 3 up in here is they're quite large, and that was by design. Again, we want to make sure that there's enough uncertainty, and we really wanted to try to capture in the uncertainty those green. But you see region 2 fits pretty well, and then underfitting at those last few years in region 4. Little different story here. This model is putting a lot of recruitment into region 4 and then moving it throughout the system. So you can see in a high PDO year, almost all of the recruitment is going to region 4, very little into region 3 and 2. And the movement rates are actually pretty high at age 4. So that's age 5. That peak right there is at age 5. And it just moves them through the system. So how this would behave if you started recruitment at 5 would be a very different picture.
Do you have any data sets that actually tell you about recruits? Are there things like, does the Alaska Trawl Survey catch small halibut, and that might give you some idea of the spatial distribution, or other sorts of data sets?
The trawl surveys do catch small halibut, probably down to age 2, I think. But the Bering Sea Trawl Survey might be a good index for those young ones, but the Gulf of Alaska survey, for some reason, doesn't capture halibut as well. It's a very different area, a lot rockier, and we just haven't found it is like we haven't. There's been many different people that have worked on trying to develop like a coastwide young halibut. They just can't find a way to stitch these surveys together. So we thought, well, let's just use the Bering Sea Trawl Survey. And when we do the stock assessment, we usually put that in and see how well it does fit. And what we found is that there's some lack of fit and inconsistencies that just suggest it's not seeing the whole picture that we need to see. So for example, 1987 year class was a massive halibut year class. And it was sort of big in the Bering Sea. It didn't show up real big, but you could see there was a little bump. Then 2005, Bering Sea saw a huge number of young fish from the 2005 year class. And we were all really excited on that one, right? And it never panned out to be a very big year class. And we often see that. And then we'll see a big bump in the Bering Sea and people get excited, it doesn't pan out, and then don't see anything, but then it turns out to be a good year class. And so that inconsistency just makes us wary of using that type of data.
Yeah. Such is the way of recruitment indices in general. But I was hopeful that there might be something in the spatial distribution that might prove useful. But it sounds like not the case.
Yeah, it's not. So what we've been thinking about, how can we use the tag data? There's some way we can use tagging data to help inform this. And so we started down that, but that's probably going to be a multi-year project. So this model is a little different, has a lot of movement. It's just sort of redistributing at those young ages. Those are the two based on the areas as fleets assessment models. And then we get into, now we're using the coastwide assessment models. And this is operating model 3. It's not much, it's similar patterns that we're seeing with OM1. And, it's fitting the end of the time series well, but a little bit off here, which does look like maybe some asymmetry is occurring. And I should note, one of the reasons we start the operating model in 1958 and not in 1923 or 1888, when we do have catch and other observations, is there are some bottlenecks historically where some of these models predict that the biomass got quite small. And it's a bottleneck in that sense. And like, you got to have enough biomass to catch the catch and get through this tiny little thing. And it becomes very informative almost to the end of the time series, which we don't want. So that's why we cut off the early years. Some of that could be going on in this model here, where it still has to get through this bottleneck, catch enough of the catch to get through there. Now, in this model, we're seeing that misfit in region 3, but this time it's a little bit more apparent, where even when we add uncertainty, and we tried adding additional uncertainty, it didn't want to, some of these years just didn't want to extend down into the data on those things. And so you can see it's putting actually more uncertainty on the upper end of that prediction than on the lower end of the prediction. So this model with its coast-wide assumptions just seems to be unable to capture that as well. And what's happening now is we're getting this underfitting in region 2 with more of the uncertainty actually below the prediction than above it. And still a little bit of that underfitting in region 4. So a slightly different look at this, but same pattern.
Another weeds question.
Yeah.
How are you modeling the spatial fishing mortality differently between, I'm assuming in the Fleets Areas model, you're taking the selectivity curves in each region and applying those fisheries in each region.
Yep.
And here you're probably just taking an overall average one and applying it everywhere, or?
That's actually a really good point, is that, so we actually for selectivity, there's some dome-shaped selectivity estimated in the stock assessment because it's using the Fleets Areas approach on the coastwide. Here we have movement, so we assume that the movement is going to account for availability, and so we've made all those selectivity curves asymptotic. But we fit the ascending limb, or we don't. Well, we assume the ascending limb from the stock assessment and fix those parameters and selectivity in here. We just don't have. When we built the operating model, we were really thinking about simulation, built in C++ for fast time and simulation. And then all of a sudden we're like, we got to condition this. Oh, we don't have auto differentiation and all those great tools, because we're like, oh, we're only going to condition it once every 3 to 6 years. Right?
Squares.
Yeah. And then so I'm using Optim and it ticks over, it runs an external executable, gets the output bits of data. And so it's quite time consuming. And it's just not as powerful as the estimation tool. Throw in the confounding, it's a nightmare. So we're fix the selectivity, but to do that, now we're fitting in a coastwide model, we're actually using selectivity from areas as fleets. So there's that little bit of consistency there from the areas as fleets assessment model. So there are some inconsistencies. A lot of these parameters come from the long areas as fleets model, because that's the most comprehensive with areas and everything. And I think that's why that model, OM, seemed to behave really well, fit really well. And then as we get to these other ones, we're taking some assumptions from that, inserting it here, and that's where a lot of the misfit does better. So if I had a lot of time, I would really want to rewrite this model in something like TMB and see how it still performs in the simulation aspect. The idea I'd really like to do is have it with templates on the parameters so you can turn on and off auto differentiation to make simulation fast, but that would be fun in my spare time.
AMB used to have guys doing that. Did that not come through?
No, it never fully did. Yeah, I tried some stuff with, templates and C++ functions, but yeah, I remember talking to a lot of people about that. It just sort of never came through. You really had to.
It's too bad that was a nice feature.
Yeah, it would be a great thing, and to be honest, I do want to do some experimentation with TMB, see how it performs, because I know ADMB really slowed down in simulation because it was doing all the auto differentiation. And that's why we just went pure C++, but
You can. We've done some of that stuff in a couple of different ways using TMB and R.
okay.
That's because the nice thing within R is you can call the function both in a TMB sense or you
Yeah,
can
right.
not. And so if you don't basically use it after it's been through the make 81 statement, it doesn't have any derivatives associated with it. Just basically call it. And so you can basically get your distributions for all your parameters and then just feed those into the model. And if you have another part that says tack on a whole bunch of extra years, then basically what you have to simulate is the recruitments and any future covariates you want to have drive things.
And that's exactly
And
what we're
then-
doing here.
Yeah. And so it just basically makes for a little bit of extra stuff. And so the way I've set it up before is kind of that two-stage sort of thing. The first part is sampling from the posterior, and the other one is what's the future going to look like.
Right. Yeah, and that's great. And thanks for that. I've been thinking about that. I'm still learning TMB and R and TB and how they all interact, and
It goes straight to RTMB.
that's what we're hearing. So and so you'll see there's a request to develop an estimation model from the last SRB. So I started experimenting and creating that. And as I was creating that in RTMB, and I'm like, man, and keeping in mind in the back of the head as I'm creating this estimation model, it's like, this is what I got to think about to create a whole new operating model. So I think that's been really helpful getting me down that road too. Like I said, it's that time between focusing on getting the operating model conditioned. I just didn't have enough time to rewrite it, do all that as well. So, but it's in my mind, and maybe we can set some time aside. Especially, I think AI can help speed up that process as well.
Yeah, if you need some help with at least the beginning parts of doing RTMB stuff, I'm happy to help, because some of just initial stupid things that you naively do that break RTMB there's several of them that are really painful to realize. Oh, I can't initialize all my object NAs because
That took me a week to
RTMB
figure out.
would fail and not do anything, and not give you a message that says you're stupid. You have to fill these with zeros. It's or something.
That one took me a week. I was so frustrated, and then I even told Ian. I said, "Man, this reminds me of the ADMB days when you found out you couldn't indent that one."
Yeah, no, it's very similar. And so that little initial learning curve of stuff is, once you get past that, it actually worked pretty nice.
Yeah, and then the other thing I did learn is that using AI helped me get over some of those humps too. It didn't give me the right code, but it identified where things were causing wrong and gave me suggestions. And then it was like, oh, so yeah.
It's impressive given that there can't be TMB code for it to train on.
I was actually surprised. It's funny when I was, because a friend of mine said AI, and he thought, we're going a little tangent here, but I think this is really useful, is that we thought, how would AI create an estimation model, simply structured model using RTM? Actually did pretty well. Didn't come up with the right answer, didn't work. But what was really interesting as I was looking through the code, I'm like, oh yeah, that's from Wayne. Well, that's an idea from stock synthesis.
Oh, really?
So I could tell where it was pulling from. So because there's not a lot out there, you can sort of get that idea. Yeah. So yeah, anyways, I think that's a great idea. I'm really curious to see, once putting this into a more powerful estimation framework, if we can do better and have faster estimation and then explore more of the concepts on the condition. All right, so the big issue here is, again, this region 3 misfit showing, and it's sort of causing, because it doesn't fit those end wells. And again, we'll talk about this in summary. It's not a lot different than the other operating model, or at least OM1 here, which was also a longer model showing about 80% recruitment to the area 4, region 4, and then some to 3 and a little bit to 2. And then again, a lot of movement as they're young, which could just be redistributing that to have a starting point for them. OM4, this was the fun one. This is the short coastwide. This one took a long time. I played around with this a lot. And what I finally realized is look at the assessment in blue here. And you see that there's actually not a lot of uncertainty. All of these plots have the same Y scale that you've seen. So this stock assessment model had less uncertainty, and that's because the female natural mortality is fixed in this model, whereas all the others it's estimated. So it doesn't have that little bit of to add uncertainty to. What happens when I'm trying to fit to this in a likelihood context, because I'm using the actual estimated standard error from the stock assessment spawning biomass, it's very tight. And so that just causes us to fit it. But then it's a very different behavior. The operating model is using the same natural mortality as the stock assessment, but it just couldn't fit that same shape that the stock assessment was coming out, even when fitting to only spawning biomass. But nevertheless, given that this stock assessment is showing a tighter uncertainty, I think we have a pretty good shape on the spawning biomass fitting there. And this is one of the more pessimistic operating models. You can see spawning biomass in the operating model is still declining a little bit while the stock assessment is starting to level. The fits to the distribution are similar to OM3. There's a little bit more uncertainty in this model. But this has a very different picture now of recruitment and movement, where it is almost a lot more recruitment is occurring into region 3. And the movement, you can see here, at least it's extending out into some older ages where it didn't seem to be quite as much as, but still not a lot.
It has less net movement than the other ones too.
Yeah. I think you're right. And that's where some summary statistics of movement up to a certain age would be helpful to see that as well. So those are the 4 operating models, and here's all their spawning biomass on the same plot with the same Y scale. And so you can get a picture of what each of them is telling us. And so you see they have slightly different shapes to them, but not totally different, and more uncertainty when you're fitting to the short coastwide on the right. Those are the 2 short assessment models. So those OMs seem to have maybe a little bit more uncertainty associated with that. Yes, trouble fitting. Something I just put together, boy, I think I just put this together last week too, is the spawning biomass by each region. And so in green is region 3, in red is region 2, and blue is region 4, and then purple is region 4B, where purple 4B is really small, and you would expect that. It's not a lot of biomass. In fact, 4B is, we thought it was its own stock, but the work that Andy did on genetics said, no, it's connected in some way. But each of these models predict a lot of biomass in region 3 and similar biomass in recent years between 4 and 2. And so a little bit of history on exploitation on this stock is that when the IPHC was formed in the 1920s, most of the exploitation was happening in regions 2 and 3. And then as time went on, exploitation moved up into the north more so. And so there was still, 50 million pounds being taken out of region 2 and 3 in the 1920s. Just quite a bit of biomass being pulled out of those areas.
Was there ever a region?
There was at one time. What was?
Back in the day,
It's like Baja.
Yeah, those are now called California halibut. No,
Have all these translation tables, like how, like from depending on what year or how the area is called, what would be mostly in the current days, but not 100% matching. You can, there are maps that change over time, different naming, and it's not always to ABC. You could spend like 2 for a long time on its own, separated.
yeah, I don't remember the history of region. So those are regional spawning biomasses, and I just want to take a pause and have a little bit of discussion about this. So we feel that all of the models are really capturing that trend in spawning biomass, which is important because the real goal over the next 3 years at least is to investigate coast-wide concepts, coast-wide management procedures. And the commission at the annual meeting, the 102nd annual meeting, actually put in a note. You'll see they put in some statements about a work plan for the MSE, and then they followed that with a note to not investigate distribution of the mortality limit across the regions. And they just don't want to go down that road right now. And have an offline discussion how it's just really challenging. So we're really focusing on coast-wide stuff. So we feel that this operating model is capturing that coast-wide. Theoretically, we could have probably just built a coast-wide simulation model, but this framework was already there, stuck with it. OM4 showed some inconsistency, but that's the really different assessment model as well, and we just couldn't get it to match it better. Now, the elephant in the room is that misfitting of the last 4 years in Region 3 especially. And so if we fit only to those data, it still couldn't capture that. So there's something about the model that's not capturing that. So as a reminder, movement can change based on the PDO regime. And recruitment distribution can change based on the PDO regime. And inserting that PDO regime really helped fit the whole historical time series that we've seen in the past. But so our thought is that something has changed with the behavior of Pacific halibut in the last 4 or 5 years, and it's not being captured appropriately in the modeling. And so one thing we thought about, well, the PDO has actually, there's a paper by Mike Lizzo talking about how the PDO becomes less correlated with some other environmental covariates it used to be correlated with. So there just seem to be differences. The PDO has been mostly low in the last, 15 or so years? Yeah, almost 20 years. And, but we've seen marine heat waves up in Alaska. So there's all these sort of new, maybe novel environmental relationships going on in the West Coast. So potentially there's some sort of change out there that we're not capturing in the modeling. But as you said, a lot of this is looking at the mirror. We're not just know until we get some observations about this. So we haven't tried to do anything in the operating model to do that. We could add it some time thing or something like that. But yeah, and I do want to
There might be ways to, though.
Yeah, I want to point out something. It is hard to see, but you see that data point in Region 3 too. Is we've seen a similar pattern in the past where it sort of misses those points, and then it was really off this one year. And I think that was the year that I conditioned the operating model. I got really worried about it. So we redid it again the next year, and then it became right in line. And so there's just a lot of uncertainty. There's this interannual variability that the model is also not capturing. So you see it comes right back in line, and it's in line for at least 3 years, and then it goes off again. But so maybe this pattern's been happening longer, suspect, or maybe we're just not capturing some sort of interannual variability. Maybe it has to do with sampling time. Maybe there could be some other explanations out there. But you were saying, Mike, there might be other things that we could do.
Yeah, but bigger picture here, the way I think about MSC is you really want to try to use it to make sure your management system is robust to what you think the major uncertainties in the system are. And so that was, as I was reading this, that's what I was going through. It's like, based on what I've seen, do I think you're capturing the major uncertainties through these 4 different models? And so to me, the 2 big ones are just the spatial dynamics, which I think you're getting at being more comfortable, especially with that last plot that I think I didn't understand before.
Oh,
about the
okay.
Biomasses in different regions,
Yeah.
and different trends. But the other one you're not really getting at this is time frame productivity for the whole stock. And I think that's the one that the commission's probably most grappling with, whether they say it in that way or not. It's kind of like, well, what does the future hold for halibut? How do we manage in light of that? And that's the part where I might consider expanding some of the operating models you're doing to try and explicitly incorporate time frame productivity.
Okay. Yeah, I mean, I'm in complete agreement with you, especially about robust. You're just trying to capture that uncertainty, make sure you're simulating uncertainty to make sure your management procedures are robust. And you mentioning productivity, we'll talk a little bit about productivity. There's 2 aspects of productivity that I haven't talked about here, and that's they're really, I think, the 2 major components of productivity, and that's recruitment and weighted age, size of age. Those are, well, size of age is captured differently, and you'll see how influential that is in the uncertainty being projected. Size of age is actually simulated as an external process, where it's just a random walk. We've seen huge changes in size of age. I think I have some slides on that. And it's simulated as a random walk changing over time right now. Really simple way to do it. Been looking at the alternative ways. But it, and so.
That's why some of your simulations go off into crazy land.
Oh, yeah. You see the spawning biomass, it's huge, right? And that's just because it can walk all over the place. I put bounds on it to keep it in like within 3% of the observations that we've had or something like that. And so I think that captures a lot of that uncertainty. And then recruitment with the PDO simulated as positive or negative, it changes the average recruitment. And so that's trying to capture the changes in productivity as well. But I think there is, in terms of, the uncertainty in recruitment distribution and also in the movement, maybe there's some other things that we could be doing.
Yeah, the other part with that is specifically for productivity is the covariance between growth and recruitment. If there is something there between them, if their beating models is independent right now, but that doesn't really describe the old data well, especially when simulating the future. Weird places.
Yeah, and so that, as Josette mentioned, that is a major, or one of our main focus on research in the future is understanding growth. So we want to try to learn as much as we can about those things as well. We've had a lot of students work on growth, size of age over the years. Nobody's really pinned down any real specific processes associated with. So that's, I think, at one of the previous meetings, the SRB also identified size of age as being one of the main future focuses for research, and that will hopefully improve projections as well.
Yeah, this seems maybe unlikely, but we've spent a lot of time talking about with FIS the potential for bias to start creeping in. Stents design. It's possible the data are wrong.
That could be as well. We have, those are designs, those 4 years are designs that we produce, not covering the entire area. A couple of those years, I believe, similar areas were being surveyed, but we had a good survey last year that went to some new areas. And then 4B has actually been surveyed, not surveyed in all years. And I think when it has been surveyed, it's had few observations out there. So there's definitely concern about bias, especially when we're talking about distribution. Coastwide index is probably likely still good, but when we're starting to drill down into specific areas.
But yeah, I mean, that's what we're looking at here. It's not a concern about the coastwide, but just those regions.
Yep.
And it's trading off the two regions.
Yeah.
Yeah, the interaction between this and some of our previous discussions got me thinking of, well, how much time during catchability is there in the survey? If so, to what degree are changing whale distributions and abundances affecting the long line survey catches? Or anything like that, it could be feeding into it, and it.
There's a slide coming in Ray's presentation about how recently things were sampled. There's definitely some gaps, as Alan mentioned in 3A. In terms of whales on the survey, we have pretty strict criteria. So we omit the data where there was really any chance of manipulation in order to avoid the chance of bias. We'd rather have variance than bias. So we have the criteria are that basically if there's a sperm whale anywhere around during it's out. And if there are killer whales and any indication of depredation, usually the killer whales, there's some damage on something that's visible. So probably less likely to be biased by whales on the survey. But the reduced design in recent years can definitely be a factor when you drill down to the level of tool.
What about competition?
So we correct for a competition. There's a whole analysis that deals with the competition. It's probably not perfect. The fundamental assumption is that all species are competing at the same rate. Hooks. And so if one of them is a better competitor, then it starts to break down. But there's been several different groups that have competition, and our method is pretty consistent. It's the state of the art. It's not a perfect correction, and it doesn't work obviously if 100% of your hooks are saturated. But that rarely happens because we always put out at least 400 hooks and sometimes as many as 800. So we don't usually get full saturation the way 5 hooks down, the saturation is going to be major.
Yes, some timers would be the way to.
And we've actually got a publication coming out with Dr. Mark Lamelli, who's done now 3, he and some PEEP students he's working with, we've got 3 different field trials where we've got several hundred timed observations. Yeah, it's kind of interesting. The early indications are that halibut and at least yellow eye rockfish don't have a very different curve in terms of their capture rates on the hook.
But I would say the sorts of discrepancies you're seeing between the model and the data points you have here are what I have seen every time I've tried to do a spatial model.
Okay. Yeah.
You
Yeah,
get,
that's true.
and actually they're smaller than a lot of the models that a lot means sounds like I've done a lot, but I've done like 3 or 4 of these trying to do them spatially, and they always have, all of mine have worse misfits than the newer students.
Okay.
It's, to me, it's more just broader base. Do you think you're capturing the hypotheses you really want to capture in those models so that when you're looking at things, you're going to be robust to those uncertainties? Because there's certain uncertainties. It's easy to do. It's like, oh, the parameter uncertainty from the model, we can just draw from the distributions and get that. But the broader structural ones that, oh, our model's wrong, how do we develop one that represents an alternative hypothesis? Those are the key ones that I think you really need to kick the tires on.
Yeah, that totally makes sense. There's a few more slides on conditioning that I want to present, just to give a little bit more insight. The first thing is the PDO that we've been talking about. And you can see in pink are the negative and green are the positive regimes. And so you see we've been, the way that we've just defined a regime is it has to be more than 3 points in the opposite. And so it's been negative here. We hit 3 positive, but then went right back to negative. So we've remained in a negative regime for this time period. But what's really interesting is that 2025 point, which is the average annual of all the monthly observations. It's the lowest that we've seen in this series. So here we are with one of the lowest PDOs we've ever seen, some marine heat waves that are occurring. You know, it's just like the environment's just really mixed up its way in this region.
And so this is the part where I was mentioning potentially doing something different rather than having a binary positive negative. My next step would be what happens if you do a linear relationship with PDO state and just see it, because that's one of the things that kind of falls out of the misfits is that on the most extreme years, is at least recently, is where you see your deviations.
That's a good point, is that all these 4 years are pretty low PDOs. So Ian has done some, Ian's done some analysis, you know, relating the PDO back to recruitment. And what you found that just linking it to average recruitment with the regimes is what performs best for the stock assessment. But now we've taken that concept, tried to link it to movement, recruitment, distribution. So we could probably just there.
I'm just looking at that time, we're supposed to do a break at 2:30. Is this a good stuff?
Oh, where are we? Oh, yeah, sure. Sorry.
No, that's fine. We've had a good discussion about it, but I'm
Yeah.
just, if there's a stopping point coming up, we should do it.
Just a couple more slides and it'll be a perfect stopping point. So once we have these 4 individual models, we integrate it into one. And of course, we're projecting each individual trajectory from this bootstrapping in each individual 4. But I like to look at, to get at the idea, is this capturing the overall uncertainty, the overall trends, and what we believe is happening. And so this is the integrated spawning biomass, coast-wide spawning biomass. And I think that is capturing what we believe is happening out there pretty well. And then again, the new plot, the integrated regional spawning biomass, and see here you can see there's a lot of uncertainty within the regions. So that those regions are translating into a coast-wide, but that we have a lot of uncertainty in what's happening across the region, except for 4B down here. That's pretty small all the way across. Yeah, it's really tiny. So then the last slide before we take a break here is what are the next steps? Well, that's the conditioning process. Now we want to really compare the new OM and see how it performs in its projections. So we want to compare what it looked like compared to the previous OM that was conditioned, what it looks like compared to the immediate term, so like the next 1 to 3 years that the stock assessment is projecting. How does the OM compare to that? Are they diverging there all of a sudden? Because that's, you know, where we ended the conditioning process. We want to make sure that that's doing well. And then we want to do projections with no fishing and different SPR values, start seeing those outcomes. And then actually start the evaluations after that point. And then the next steps are also, there's 10 more other items in the MSc program work. So those will be a lot faster than this. I really was looking forward to talking to the SRB about the conditioning. And then the others are just sort of insights into what we're going to be looking.
Yeah, that was super helpful. I've seen the whole background on the conditioning.
Oh, good.
Or at least it's been a while.
Yeah. Right. Cool. Well, thank you so much. And I think after that, we will jump right into the program of work. It's good stuff.
Welcome back, everybody. Back to you, Chair.
All right. Okay, so that's the conditioning. So before I go on to the rest of the MSc work plan, and this is really a work plan for the next 1 to 3 years, you might say, is the commission, we had a really good discussion with the commission at the annual meeting, and they came up with some high priority topics and some low priority topics, which are in the annual meeting report. I'm just going to skip over these because I summarized them later, but I just wanted to have it in there, the full language of them. There's 4 high priority topics, and then there's 5 low priority topics. And then you'll see I added a couple more low priority topics because just never think I have enough to do. I mentioned some other notes that I just wanted to point out because this is important. In the annual meeting report, there's a note that the 2026 MSC and Harvest Strategy Policy Program of Work should not include topics related to the distribution of the TCY, as this is part of the decision-making process. That's really good guidance for us to have from the commission and really helped at the MSAB meeting. And then just noting that the Harvest Strategy Policy has just been adopted, but there's still some questions that the commission's had, and with the new operating model, the full stock assessment, reconditioning of the operating models, they left a couple of items to be investigated pretty quickly, and that's basically what's the appropriate fishing intensity. They may make a change on that pretty soon, given the new information we have. So they may update that. So the 4 high priority tasks: condition the MSC operating model. We've already talked about that. Evaluate a range of fishing intensities, investigate productivity regimes, and then further develop this depleted concept and identify a limit reference point. So I'm going to jump in and start talking about fishing intensity. So one thing, now that we've reconditioned the operating model, we've had new understanding of the halibut population. We have updated the maturity curve, and it's probably a good idea to check that the reference fishing intensity, which is a 43% SPR, is still the optimal management procedure fishing intensity to use. I do note at MSAB 21, which was a year ago May, there was a recommendation to evaluate a range of SPRs. And I think the year before that, they actually made a recommendation to update the reference SPR to a 46%. So they found some MSC simulation results back then. They suggested to the commission to do that, but since we're still working on the Harvest Strategy Policy, the commission decided to wait on it. So this is about time. It's a good time to do this. And the MSAB has actually made a recommendation on SPR rates or values before. They updated that at MSAB 22 last week, and it's these same values with a 1 or 2 more added, basically. So I think this is a reasonable range, and that's where we'll start. But as time allows, we always try to fill in these things and get better drawn curves and things like that.
Seems like a pretty conservative range.
It is.
Nothing below 40%.
Yeah, it is. And we talked about that at MSAB, and they're like, well, we're not really interested for a reference management procedure. They're not really interested in going much lower SPR, higher fishing intensity than that. But my own interest is going at higher fishing intensities because MSY proxy right now is 35%, or MEY proxy. No, that's MSY proxy. Is 35%. And then you'll see there's an item on here to re-examine MSY based reference points as well. So we'll examine all of that.
This might be too much for right now, but how are you currently handling time varying growth as part of your exploration of SPR reference points?
As time varying growth, so the way the operating model is built and the assessment as well, we do not have length and translate directly from numbers to using a weighted age. And so the operating model, because weighted age has changed so dramatically over the history of the stock, that we just project it with a random walk. So it's basically integrating over a range of potential weighted ages and incorporating that as part of the uncertainty in a real simple way. But you'll see also in a few slides that we want to investigate specific assumptions about that, like low weighted age, high weighted age, and see what the outcomes are. So So that's the SPR values. Your question gets at investigating productivity regimes. And so I pulled it out in the interest of time, but I was just thinking it'd be nice to have a little background here again. Basically, we've identified two major sources or two important sources of productivity, influencing productivity of Pacific halibut. That's size at age or weighted age, and also average recruitment. There's a lot of variability around average recruitment, but the level of average recruitment can change according to the PDO. So we want to explore three main concepts here related to productivity, how the population and fisheries respond to different productivity regimes, meaning how the how the spawning biomass changes across these different productivity regimes. What would be mortality limits for the fisheries, things like that. The second one, I think, might have been getting at what you're asking, Mike, is the optimal reference fishing intensity. Does it differ across productivity regimes? When the weighted age is low, is an optimal different than when it's high? And then also the commission is interested in how can we incorporate productivity into the management procedure. And this is, we've seen this in the past. A lot of people have done research on this with mixed results coming out of that. If you're really good at knowing what your productivity is, then you're probably pretty good at managing onto that. But when you get it wrong, it's the problem. But we can do those simulations. That's the fun of MSE.
Alan, so it seems like you're just talking about changing productivity, right? Not actual regime shifts of distinct constant.
It is here to actually set it at, when we talk about productivity regimes and exploring it, we would set weighted age at a fixed low values and the PDO at, say, a fixed negative. And so that would be a low weighted age, low PDO, which means low recruitment, different.
Right, you are talking about a regime.
Yeah, so actually fixing it, and in the document, I'm surprised I didn't put in this, but I think I was trying to pull stuff out because it was getting long. In the document, there's a plot, I call it the purple trace plot. It's purple, it has a really wide range of purple spawning biomass, and that's showing integrated over high and low productivity. And then it has a little thin green band, and that's a simulation forward in time with the same fishing intensity under a low weighted age, low recruitment scenario. So it's really trying to partition that bigger uncertainty into how much uncertainty is from these regimes. And what we found is that a lot of the uncertainty comes from these regimes, and most of it from weighted age.
Yeah. Which figure is that?
Yeah, I don't have it in here, but it would be figure, I was just looking at it. It would be figure 17 in the document, and then figure 16 would also be a useful one. So this is section 2.1.
Thanks.
Yeah.
Yeah, wow.
Yeah. It's fun. I was always worried about investigating productivity because the idea of MSC is to be robust to the uncertainty, and productivity is part of the uncertainty. And I didn't want to get away from that, but I think as I started investigating it, it does have some useful insights. So
I can't remember, have we ever seen just surplus production time series?
we've done that in the assessment.
We've done the assessment.
Yeah, we've done it in the assessment.
At least that's a deja vu.
Yeah, yeah.
It's been a couple of years.
And one thing in the decision table for the stock assessment, there's always a column that is to 3-year surplus production. What fishing intent or what catch level, what amount of mortality would result in the same spawning biomass, 50% chance of the same spawning biomass in 3 years. So keep the spawning biomass steady.
Assuming that it's positive.
Yeah, which we found a few years ago, there was hardly any, but it's actually getting
It
better.
hasn't gotten there.
We haven't.
There was a couple of years. It's negative, yeah. And historically, there was a long period where it was negative in the early 2000s.
Yeah, I'm sure it was. So to investigate productivity, one, we have to define what the regimes are. So we've already defined these, but we'll take a look again at weighted age and PDO and see if that, make sure that's a good way to define the productivity regimes. We'll use the new operating model to conduct simulations, fixing productivity or fixing weighted age and fixing the PDO. And then evaluate the effects of these productivity on the fishing intensity. And so those are the first 3 steps that we'll do, and then we'll move on to the other ones, is thinking about management procedures to investigate that incorporate productivity, and then also determining methods to present the effects. I've been trying to work on some methods to do this. I'm not real happy where I'm at with this purple-green plot, whatever it is, and I want to put some tools in the MSC Explorer where people can be a little bit more interactive with looking at how productivity affects the outcomes.
One thing I think you might want to consider as part of this is the joint distributions of different aspects of productivity, as well as pulling maturation into it too.
Oh, okay.
And so it's like, well, if your average level of recruitment is the same across all of these, fine, that's great. But if your average level of recruitment is varying with these as well, then it's probably not as useful to explore cases that have never happened in the past, like great recruitment with, I don't know, outstanding growth, or great recruitment with really poor growth, or whichever ones don't happen, they're not as important to look at. So it helps you reduce your universe of things.
Yeah, and I think we've seen it all.
We've had great recruitment and high size at age, and we've had low size at age.
Well,
Yeah.
if you have it, that's
Yeah.
great. But
Yeah.
looking at some of the covariant stuff to make
Yeah.
sure you're doing things that are relevant with what you've observed historically.
I really like that, because that's also why we don't do the grid type search on the MSC operating models, is we don't want to have those combinations that are really unlikely. Right. So that's what I have on investigating productivity. Talk a little bit more about that when we get into some simulations related to depleted. But first I want to talk about this depleted concept. So Anne Marie, the science advisor for Canada, brought up this concept. People are very interested in this. I'll give you a little bit of background on this. I'm going to explain these plots as we talk about the background. So we use dynamic unfished spawning biomass in our relative spawning biomass calculations. So we have spawning biomass on the left, and what you can see in the black line here is our estimate of what this unfished spawning biomass would have been in the stock if we had not fished it. And that's basically due to changes in productivity, changes in recruitment, changes in weighted age. And you can see that in the early 2000s, it peaked, but has been declining pretty much ever since. And as Ian mentioned, there's this period of negative surplus production during that time, where the unfished spawning biomass, the spawning biomass would have declined regardless of whether we were fishing. The blue line here is our best estimate from the stock assessment, sample stock assessment, of the spawning biomass with fishing. So this is our best estimate of what actually has occurred. And then if we take the blue divided by the black, we get the relative spawning biomass. So what people have been noticing is that our status, relative spawning biomass, is good. It's around 38%, something like that, and it's increasing. Yet the spawning biomass is at one of the lowest spawning biomasses they've ever observed. So people are finding this sort of conflict. Yeah, yeah. And so they're asking, well, how can this be? How can we be perfect status and at a low spawning biomass? And so the SRB helped at the last meeting. We wrote a couple paragraphs that are in the harvest strategy policy. During the offline session, I actually wrote those paragraphs. It was super helpful.
That's great.
Yeah, I really, really appreciated that. Very helpful. We defined this, so overfished is a concept defined by the relative spawning biomass. Overfished is a concept measuring the effect of fishing and not the effect of the environment. So you can come out of an overfished situation with management. Management will get you out of an overfished situation. The concept of depleted now is a concept related to absolute spawning. And that's how the weight of fish out there, the biomass, the reproductive potential of the stock out there. And this accounts for fishing, but also potential effects of the environment. So if it is in a depleted state, you may not be able to come out of a depleted state solely by stopping fishing or by management action. But I think it's an important concept to be aware of, in that we're looking at defining a limit below which we don't want the spawning biomass to be below, because that could be, well, the way it's phrased in the harvest strategy policy is the potential for recovery is certain. We get to a small enough spawning biomass, maybe there's consequences to that. So those two concepts, where overfished is over on the right plot as a constant percentage, which translates to a moving actual absolute spawning biomass, whereas depleted is a constant level of absolute spawning biomass that we don't want to go below, which then translates to a varying status for relative spawning biomass. So we have an overfish determination of 20% relative spawning biomass. It's in the harvest strategy policy, but we don't have an actual level of depleted that we want to be below. How do we define it? We can define it, I think this next slide. Oh no. So we can define it as what's the lowest spawning biomass we've ever seen and have recovered from. And that would be 2024, the spawning biomass in the last 2 years ago. So we don't know that we've recovered from it, for one, although I think it's very likely we will. And two, once we say, well, that's the lowest spawning biomass we've ever seen, what's an appropriate level to define depleted as? Do we not want to be below where we've been in 2024 ever? Or is it half of that or whatever? So what we've proposed, and we presented at the last SRB some sort of pilot simulations, is conducting simulations using the operating model to identify a depleted limit reference point. And this is basically a level of spawning biomass below which recovery would be certain. So the way that we do this is we define a worst case scenario, and I'll talk about how we're going to define a worst case scenario, what that means. Define a worst case scenario. We simulate forward in time for, I think, 40 years is what we did last time, with a high fishing rate. So it's driving the stock down. It's driving the stock down to some level of spawning biomass. We don't care where it's at as long as we get down. Stop fishing, except for, I think, 3 million pounds to account for bycatch and subsistence. We stop fishing, and then we see over the next, say, 40 or 50 years, does the stock actually recover, to increase and recover to a level? What we found with these simulations here on this plot, that when the stock was driven to, I think it's around 90 million pounds, all of those trajectories did recover. When it was below that and maybe above 40 million pounds, some of them recovered, some of them did. And then below 40 million pounds, none of them recovered. Now, what's the worst case scenario? So we want to do this for a worst case scenario so that we can be certain that this is a plus limit reference point. So we defined it, one, as low productivity, low weighted age, and low recruitment, low average recruitment. And then we put a depensation on the stock recruit curve, and we chose a value of depensation from a previous analysis we did, a year or two ago. So we chose a single value of depensation. And we used those two concepts to define a worst case scenario. And then I think, as was mentioned at the last SRB, this limit reference point might actually be defined by the depensation. So we we'll check for all of that.
It should be.
Yeah.
That's the whole problem with
That
it,
is
you're trying to
Yeah.
make something out of something you've never observed.
Yeah.
And so it ends up relying on your assumption that you didn't.
Yeah, so we're thinking, okay, well, that's interesting, but maybe we'll take a look over some different values of depensation and maybe some different productivities to sort of just see what's happening. But the MSAB actually brought up a third concept that would be good to investigate as well, and that's the fecundity relationship. If that is, is dependent on size, where larger fish are more, have more reproductive output, that would affect these simulations as well. So do I have it here? Yeah, so the SRB made a recommendation from the last meeting to conduct these simulations, but increase the sample sizes so we get a nice smooth curve here. And then I think offline we talked about, well, take a look at what your assumption on depensation actually means to this, and what reasonable values of depensation.
This is going to be a really tricky thing to do, or at least you can simulate a lot of stuff and generate lots and lots of results. I don't know how much new understanding it's going to give you beyond some fairly simple, dumb sorts of things.
Yeah.
We tried to look at some of this stuff for blue crabs a while back because there was concern about potential sperm limitation and how that might drive the stock recruitment relationship to change. So we did some stuff into it. Ultimately, we decided the best we could do is say, well, we have a knife edge response below the lowest sex ratio we've ever observed.
Right.
And so then that drives everything.
Yeah.
And it's like, yes, we could put it lower than that, but we don't think it's higher because that's not consistent with the data.
Right.
But how much lower is it actually? And so, and those sorts, I haven't come up with a way to do any of those in a better way. And at least the meta-analyses I'm aware of that have tried to look at depensation are, you just don't see it very often. So I don't know how well you can generalize it.
It totally depends on the modeling.
Yeah.
And Hannah and I have done different models and reached really different conclusions there.
And
Basically, from the models that I've used with Ray and other folks, it seems super rare. Not super rare, but it must be occurring at stock sizes that are below anything you would hope to ever get to. For anything except elasmobranchs.
And we did an analysis. Anna had us look at depensation, estimate it, so we took a look at, from the 100 years or whatever we have, we took a look at depensation in low average recruitment, high average recruitment regimes as well. And there were, I think, a couple of cases where it did estimate some with a wide confidence interval. And so the value we used in this initial one was from that sort of analysis, looking at all our assessment models and predictions and what's the reasonable value from that. But it still was pretty low sheet.
Yeah, there's some other ways you can induce depensation in these models that aren't ones that people typically do. And so for striped bass, we have a case where we've had a new disease that's been increasing in recent years, such that it looks like the stock is really close to not being able to replace itself, given what we think its current natural mortality rates are. And so that's kind of a form of depensation, that it's getting below this critical level where it's going to just continue to decline as long as it's getting that natural mortality rate.
As long as these dynamics don't break down at low densities.
Well, but it's one of the things I actually expect them to respond. In oysters, we've had the same thing that for 20 years, there was a period where they had this really severe set of disease outbreaks for us. And now we haven't seen it for 20 years. We have pretty good evidence that they developed disease resistance. There are remaining ones that are left, and they've been recovered since then. But though all of those sorts of things resolve around some sort of hypothesis of a perturbation that's going to happen to the system, drive it to low abundance that you want to manage to basically avoid doing even more harm when you get down into that situation. I don't know. I always think of them just in terms of individual hypothetical scenarios of what's going to happen.
And I think that's very similar to where we're at with Pacific Halibut. If we look at this plot, we have a low spawning biomass that we're currently at, and the commission has been making precautionary decisions on the mortality limit, not following the reference level that we could be fishing harder at because of concerns of the spawning biomass decline further. That is maybe the hidden objective, or maybe it's, a concern about where we're at and not wanting to go lower. But it doesn't help define that limit. Where do you define a stock as depleted and take serious management action? So what we're trying to do right now is, I think, twofold. One is to just just through simulation, are we at a level that we should have serious concern about? Is recovery uncertain where we're at right now? Simulations have shown that the stock should recover, but based on the assumptions that we're putting in simulations. And then the second objective is, what would be a reasonable limit reference point to define so that we can then have this concept depleted, but also maybe develop a management procedure that avoids getting to that level. And one thing I've been telling people I'm looking at right now is an empirical control rule based on how the commission has been acting in recent years. They've been backing up mortality limit. Is there some indication of like their comfort level indicating a control rule as we approach this limit level? So that's where I see this going. And this simulation is really the only thing that we could come up with in the short term. So maybe this is something we can talk about in our little session tomorrow as well, brainstorm on.
Yeah, I do think this is helpful because you can't do it strictly empirically. At the lowest observed, you only have one observation that it recovered, so it doesn't tell you anything about the probability.
Yeah.
It's still a mill recovery.
Right.
It's gone up since then.
Yes.
It's a weak definition of recovery.
But the status is great.
But the status is great. That is the
Yeah. And like what you're saying with the disease is that, you can all of a sudden have like a regime shift or whatever pulls you out of that state. And that could easily happen for halibut. We're doing simulations with low productivity. It's pretty easy that a change in the regime could jump to higher average recruitment, pull it out of these low spawn biomasses. So
That's exactly what we saw in the late 1970s. We didn't build up spawning biomass and then get recruitment. We had recruitment turned on, and then it turned into spawning biomass down the road from what could have been as low as we are now. We just don't have the data to tell us exactly how. So the few guys that were actually fishing out there said it was very bad.
Related to this, there was the comment from Peter Emery, I can't remember, about the commissioners wanting to know how other fishery management organizations completed.
right.
I was thinking about that. There's very few that have these dynamic reference points, so that that's not part of the U.S. system. It is part of some of the tuna RFM levels. Estimate sunfished trajectory as well. The name depleted is also part of the New Zealand system.
Yes.
But I think it's absolutely equivalent to overfished. They just call it depleted.
Yeah, in their harvest strategy policy, they mention, they call it depleted, but they mention these two concepts. They say that depleted may be caused by environmental conditions as well as fishing conditions, which is why they don't call it overfished.
But in practice, it's like the overfished. Not the definition.
Yeah, and I completely agree with you. What I've been explaining to people that are struggling with is like, well, who else uses depleted? And I say, actually, most of the US fisheries use depleted concept because they define the B0 as a single point in time. And so everything's relative to that. So if you're, whatever it is, it's not changing over time. So it is analogous to the depleted. It's actually the overfished concept that is new, which a lot of tuna RFMOs are using. I think I've been thinking about this a little bit. And I don't have a really good answer, but one thing I've been thinking is what complicates this is the drastic change in weighted age for Pacific halibut is making this like it's highlighting that there's these differences. Whereas, in tuna, from what I've seen, they may not have these big changes resulting in a black unfished line that looks as extreme as this. And so when your unfished spawning biomass is maybe changing a little bit, then you can probably get away with just the overfish level. But here we have really good status. We're doing great on relative spawning biomass, but the spawning biomass is quite low, not only because of fishing, but for other reasons.
The other way to phrase it is we're not doing very well, but we could.
That's where we are.
I like that. That's a good way to put it.
We use the depleted term for a few of our state and regional managed fisheries, largely because of cases like this where we think it's more environmental, driving the stock to a lower state than direct effective fishing. We've basically taken empirical approaches like you've talked about to trying to define that, of saying we don't want to drop below the lowest value we've observed. Or we have in one case for oysters, there's some estimates out there of what basically ecologically constitutes an oyster reef and below which we don't want to fall. So that's the only one where we have an external sort of ecological driven definition of it. I can't think of an analogy that you might use for halibut.
Yeah.
Something like that, but
Delaware Bay Oyster had a shell budget model that came up with a point of return. Basically, you use the shell substrate faster than their substrate. It's too unique to share.
Yeah. So, well, I wouldn't mind if we have time tomorrow discussing this more. I think this would be a good discussion to have in the offline session about some of the details that we could do here. And I just wanted to point out another recommendation from the SRB was defining an exceptional circumstance if the stock is determined to deplete it. And I like this because as the state is unlikely to occur under the circumstances, I love the harvest strategy policy. Like we're defining a depleted limit reference point as somewhere we just don't want to go. And it should never really theoretically occur, at least in the short term. And so I think if all of a sudden we do a stock assessment, it's declared depleted, and it's like, whoa, let's open up the whole operating model and see why this is going on. So, but I think that's good. And so we've come up with potential language here. If the stock assessment determines that the stock is depleted in 2 or more consecutive years, an exceptional circumstance will be triggered. 2 or more consecutive years is just the idea of persistence before declaring exceptional circumstance.
If you could go back though
Yeah.
to your plot of the operating model trajectories versus the ensemble estimation model trajectory.
The individual one?
No, those ones. You can see there's lots of red room below the blue.
Yeah.
And so that's the part where trying to decide what you're going to call depleted relative to what your operating model is already saying is within the bounds of normalcy is going to be tricky.
Yeah. Yeah, because
And perhaps if you need something that's based on previous decisions, maybe you can use some lower bound of what your operating model says as trying to get at a bounds for what you might call depleted.
so potentially looking at the range of these operating model outcomes of spawning biomass.
Yeah.
That would be another good thing.
Because that would also tie it more to the exceptional circumstances, normally being basically outside the parameter space you've explored in your MSE.
Yeah, yeah, that's true. Yeah, I like that a lot. Especially related to the exceptional circumstance. All right. Well, that's what I had on depleted. We want to have any more discussion on that right now? Or maybe think about it, you know.
Yep.
This would be a good breaking point, but there's a number of just individual things to talk here. So if you want to go a little bit longer today, I could break at any point in time. It's almost 4 o'clock right now. But all that I have are the low priority tasks, which were defined, the first 5 were defined by the commission. And then we added the last 2 points there in italics, just indicating things that have come up with the SRB in the past and other important things that we should talk about.
Let's go for another one-ish.
Oh, yeah, sure. Okay, so the SRB recommended at the last one to consider the development of assessment model within the MSE framework, basically improving the estimation model, and it would have multiple benefits, which we completely agree with. So we've started this work to improve that estimation model and the simulation of the assessment inside the OM. And the one holdup, the reason that we haven't implemented something real informative there right now is the simulation time of that. And we tried to mimic the ensemble assessment in the past. It's like, well, that's way too much. We've done single ones, try to do it, and it's sort of worked. And so, but I think now is a good time to reopen that and see what we can do. So I've started work on that.
Background there too is that we keep having discussions about reduced designs for the survey. Saying, well, I wonder if a better survey would actually pay for itself by reduced uncertainty. So trying to do some more value of information analysis, but that's been tricky because we don't have a good way of coupling uncertainty in the survey index, uncertainty in the assessment output.
I think I've got a couple ideas for that we might want to talk about. Apps suggest as options.
Yeah.
So the ways you could get at that are you have your whole history of surveys. You can resample from those as your smaller, more restricted version. and run your assessment models on those resampled small ones and see how much your estimates start to vary from that. That'll give you at least a minimum estimate of your uncertainty that you're getting by having a more restricted survey design. And you can, depending on, I don't know how you're including assessment uncertainty in the MSC itself, but you could basically model that error,
Right.
or you can then do another simulation study that looks at the autocorrelation in that error. You can look at basically how far off you'll get into the future and do some simulations of that uncertainty.
Yeah, so Dr. Webster, Ray, has done quite a bit of work looking at the effects of the reduced designs and increases in uncertainty. And what we've done up to this point is we've taken that output that he's created and say, look, the CVs go up like this or this, you know. Ian's done some simulation in the stock assessment and saying, what would the effect on the stock assessment be? And then the MSE right now has a very simple approach. It's not actually, it's doing more of a correlated random distribution on mortality limit instead of an estimation model. So it's correlated between the mortality limit and the status of the stock based on current biomass in the operating. So it's just putting error on that.
So it's got both the implementation part of the error and assessment uncertainty all together.
Yeah, and so that was the real impetus here is it's such a simple approach that we can't get at these things, and actually introducing a actual estimation model that inputs data would then have the benefits of what if natural mortality is wrong there? What if your data is different going, you know, all those sorts of things. So that's really the impetus behind this. But we have done some work on examining the effect of reduced survey designs. Not exactly as you've said it, but you know, taking that uncertainty, empirical uncertainty, and then putting it into the assessment, putting it into the MSE to see how it affects. And I think the SRB at last time was like, that's great, thank you. You can do it even better. So, and you know, it was one of those things where it's just a kick from behind, say, you know, actually do the work and get this done. So I think it's really, so we're working on that, and we'll see. I'm ambitious, but I'm ambitious in putting in like an actual age structured model into this as an estimate, as the estimation model, but I might back off to like a delay difference or something like that. A little bit faster. We'll see what I can get. It was also like, okay, I need to learn RTM. So that's how I started. Just let's go in and code it. So that's how I've learned RTMP now. That's where I get the bumps in the road with that, learning a lot about that. So it's almost at the point where I can test it and see how fast it is.
Yeah, the delay difference might be the right level complexity. Fit the mean weight time series as well as the elements.
Yeah, I've been a fan.
I would encourage you to make the full jump.
Okay. I mean, it's getting so fast.
It's
right?
computer time too. It's like, okay, so basically all you do is you reduce your number of simulated runs you do. And honestly, by the time you get to about 50, you have a really good idea of what's happening with the median.
Right.
And
Yeah.
for something like this, I think that's what you most want to know about.
Yeah. And then if there's one case, I could add more. We're able to use cloud computing to like split it out, you know, things like that too.
So they seem like they can be overwhelming at the beginning, but the actual assessment models you're using, I don't expect would be ones that take a long time
Right.
to run.
And yeah, and we'll do things to make them run faster. But the one thing, when we did this before, we were trying to use stock synthesis to incorporate that. And the one issue that we were really cognizant of is mimicking the ensemble stock synthesis. And a single model can get pretty close, but you know, as Ian mentioned earlier, there's some benefits of the ensemble model over time, the stability and things. that we want to try to achieve. So,
Well, that's what I mean by going the whole shebang. I
Yeah.
actually do the ensemble.
okay.
And just do it for a limited, you basically reduce way down your number of scenarios to start with. You do your most interesting scenario
Mhm.
that you have, your most likely scenario, and you do it for 20, 30, 15 runs. That's been my approach when I have something that just is gonna
Okay.
take forever to run. Is I just go way back the number of ones that I do into something that fits within my.
Yeah.
I think that's already doable because the FIST designs that we see, the potential FIST designs are,
Sorry.
but there's really just a handful of potential FIST designs
Yeah.
that are presented, right? And those would be the scenarios.
The-
If you move forward under the base block.
Right. Right. And I mean, the one issue there is, I think even like, there's so much uncertainty in this with weighted age and average recruitment changing that, I think you would need more than 50 simulations to get even a good picture of the mean one. It's just so variable. That's what I found, but we've done, I mean, I've done simulations, 500 simulations, because we have 4 OMs, you know. But yeah, I think typically I've done 500. And that's trying to characterize the interval. So 50 to 100, we could probably get the good idea.
It's 50-year median is
Yeah.
within my management tolerance anyway.
Okay,
Within a
okay.
few percent of where it's gonna end up.
Yeah, yeah, and
After
you're
50.
and you're doing comparisons too.
Yeah. The other thing you can do that speeds up your time is thinking about how far in the future you run these things. It's like, if you
Yeah,
go with
no.
Andre's recommendation of run everything 200 years into the future, it's like, I honestly don't really care if I ever get to equilibrium in the way my model is working. Because I want to know the relative differences between the models and how they behave in those transitory states is actually a part of the interesting story.
Right.
And so just doing them even out 20, 30 years, it reduces the number, because where you really run into is, okay, I've added 150 years of data to my estimation. Now it takes 10 times as long to run, or everyone does. And those things really do add up, but doing it a little bit more short forecast in the future.
Yeah, and what this model does every year that's added on in the projection is not just additional, there's additional time with every single year that keeps compounding. So it's like, we've already backed off the 60 or 70-year projections, but I think we get out of 50, we could get reasonable results. Okay, so that's really good insights on that. And I'm excited about that because that gets me back into coding. I'll go on just.
Definitely make recommendations that will help with that.
All right, excellent. Appreciate it. Let's see, I think we can get through this one. This will be good actually to finish on because we've already talked about depleted. So one of the low priority tasks is once we define a depleted limit reference for some level of low that we want to avoid, we can investigate management actions if the stock is approaching this depleted limit reference point. And noting that determining this reference point is a high priority task. So we haven't actually defined what they could be, but management actions could be a control rule that's based on absolute fishing biomass and not relative spawning biomass. And basically reducing fishing intensity as it approaches some sort of depleted limit reference point. Another potential way to do this is to adjust the reference fishing intensity based on perceived productivity regime. And that, because you're not likely to go to a depleted level at higher productivity, then maybe having lower fishing intensity when low productivity would keep you out of those low spawning biomass levels. And then a bunch of dots to brainstorm potential actions here. So I wanted to give a really brief example on what one idea I've had for a long time is using two control rules. And hesitation there is that it gets more confusing. It's challenging to understand. You're adding another axis here for people that would, just, we may not want to add more challenging way to understand this. It may just become more confusing. But I wanted to give people the opportunity to tell me what they thought about this. We presented this to the MSAF last week, and people are like, okay, it's pretty interesting. But if you had two control rules, one based on stock status over here and one based on absolute spawning biomass, how could you combine these to then offer a reduction in fishing intensity? So I give 4 examples. So on the left is control rule 1, on the right is control rule 2 or CR2. And so example A, you can see here with no reduction. A over here would be about a 25% reduction. Example B, both of them have a reduction. Example C is no reduction in fishing intensity. And then example D, there's a full reduction, basically stopping direct fishing, but this control rule says not to. Now, Dr. Pete Hulson, the science advisor for the US, pointed out something really interesting in his control rules. And he asked, did you purposely put bad on there? And I did not. It appeared that way. So something in the universe is telling me something with that. I just haven't figured out what it is. So with these different methods, we thought, well, with these different cases, examples, we thought, okay, maybe there's 3 ways to do this. Method 1 is to just take the maximum reduction of either control. That's pretty simple to do. Method 2 is to take the mean of the 2 reductions, average it. And method 3 is to combine it through multiplication and taking a combination of the 2. So it's pretty easy to see here what happens. Most of them take the more extreme approach, except for B is the interesting one, where both of them are telling different reductions. So taking the maximum reduction would result in the 50%. Taking the mean would be somewhere in between the 2. And then combining them would actually take a further reduction. So this is just to show examples of way to do this. I don't know what the best way would be. MSE can evaluate these and find out that, what is the best way, or we can think logically about what would be an appropriate way to do this. But this was just some brainstorming that we did, came up with ideas to invoke a second control rule depleted, in addition to the stock status.
Is on the left, is that the current control rule?
Yes, it's a 30-20.
Okay.
And the objective for MEY to stay at or above is 36%. That's why it's a darker. So yeah, the left is a current control rule in the harvest strategy policy, and this is a theoretical one, and which you combine the 2, just use 1. So that's one idea that we came. And then different methods to do it.
Method 3 doesn't make much sense to me.
No?
I don't understand why. Sort of double count the reduction.
Yeah, it does double count. But I came up with that as a method, like now both of your indicators are in bad areas, are on the ramp that maybe you do want to take extra caution. It's a way to add that in.
Method 1, you could make it a pseudo control rule, just have the slope, adjust the slope there.
For what's on the x-axis?
Oh, I see.
They're
Yeah,
different
yeah.
x-axes.
Depends on,
Yeah.
Right.
That's the key, is that you can be like A shows, you can be totally fine on 1 and not. So anyways, that might be a good place to stop for the day. If you wanted to get into some report writing. And then the rest, it just becomes, more high level for this. In terms of the work plan.
I mean, essentially, these different methods would be nice things to investigate in some future.
Yeah. Yeah.
You have the board to see.
I know. That's the fun part about this. I think people are realizing that. It's like, oh, well, we can test these things out. Value.
You don't have to guess which is the better method.
Yeah. Yeah.
From theory.
Yeah, right. We just got to come up with the ideas. Keep you busy.
Well, it's great to be in a position where you're not trying to coax them anymore into adopting a harvest strategy policy, and instead
yeah.
they've done that.
Yeah.
They can start working on the wishes.
I know. Yeah, it is. It really opened up my mind and what we're starting to think about. So it's great. All righty, stop there then.
It's good.
Okay. And we can pick this up. I imagine 20 minutes more.
Okay, we'll probably start first thing with that.
Okay.
Okay, I'm going to stop the meeting, the recording, the online meeting, and the board is just going to jump into a drafting session on the report. So for those listening in online, we'll reconvene at 9 a.m. tomorrow morning. And the chair will give a quick recap of day one, and like we can review any text that you wanted to, otherwise we can just progress to the rest of the meeting. So thank you very much, everybody. See you at 9 a.m. tomorrow.
Thanks, Dave.